we started our discussion last week on time, equity, and risk, and we're going to continue the discussion. So this is the second to last lecture, and this is the agenda for today. Last week we already talked about the Ramsey rule. We started with saying that climate change is a long-term problem, a global problem, an uncertain problem, and you do not need to care about climate change unless you care about the distant future, faraway lands, and remote probabilities. So last week we talked about the Ramsey rule, and a key part of the Ramsey rule is that that's the eta G, is that you make a trade-off between your current poor self and your future, hopefully richer self. And today we're going to talk more about those trade-offs where it's not your current poor self versus your future rich self, but we're also talking about trade-off between the current poor and the current rich. And we're talking about trade-offs between fortunate futures and unfortunate futures, right? A future in which you're rich and a future in which you're less rich. And the same curvature of the utility function will pop up again. So I derived the Ramsey rule, said that we discount the future because we expect to be richer and therefore happier, but also because we are impatient. And then I said, well, discounting matters. It really drives the social cost of carbon, and it really drives your optimal emission control, as we saw in yesterday's seminar. And then I said, well, yeah, this is sort of the theory of saving, the theory of investing, but how to pick these parameters, because they are so terribly important. And that is sort of where we ended, that if we observe people, we find that they are terribly impatient. If I ask you, do you want to see the England-Senegal game tonight, or do you want to wait till Sunday? A number of you will say, well, give it to me tonight. Other people don't care about football altogether. But if I ask the question, do you want to see the next season of Stranger Things this weekend, or do you want to wait till next summer? Those who care will say, oh, I really want to see it now, right? So we are impatient. At the same time, we have a lot of ethical and religious reasons why we should not discount the future. And that creates a real conundrum, that what do we do here? And particularly, what should the government do here? Because on the one hand, we want the government to sort of reflect the will of the people, not fully, right? The reason that we have a government is also to provide public goods and to protect minorities and those sort of things. And in that sense, we want the government to act differently than we would as private citizens in a free market. But at the same time, we want the government that sort of like follows the will of the people, right? We don't want a theocracy. We don't want the government to say, well, because Socrates said and Aristotle wrote that usury is bad, that therefore we should not discount the future. They did write that, and St. Augustine picked that up, and therefore for a very long time all Christians believed that you should not charge interest, that is, the discount rate is zero. And of course it wasn't just St. Augustine who picked this up, but also Mohammed picked this up, so it's written in the Quran that you shall not charge interest, that is, you should not discount the future. We don't want that sort of government to tell us, yeah, the Quran says this and therefore we shouldn't do this, right? That is not the sort of government that I personally would like. So we have a real conundrum there. So people are impatient, therefore they discount the future. We want the government to sort of follow that will, and that means that a problem like climate change is not important, right? because it's mostly in the future. We also want to somehow have a form of discounting that follows the empirical evidence without discounting the far future. And then, of course, we also want these rules to be consistently applied across public policy. We do not want a high discount rate for investments in education and a low discount rate for investments in greenhouse gas emission control. That would be utterly inconsistent. And the question is, can this be done? And of course, I would not ask this question if there is not at least a start of an answer there. And the answer lies in so-called declining discount rates. Now, the starting point is our conventional constant discount rate, which is known as geometric or exponential discounting. Exponential is the mathematical form that you see. Geometric processes are exponential processes according to the jargon of mathematics. And our conventional discount rate has a very peculiar property, which is seen if we look at the relative price of time rather than the absolute price of time. So you can see sort of the discount factor, 1 over 1 plus rho to the power t, as the price of time, right? That is essentially what it is. This is the price we attach to future happiness, essentially, because this is a utility discount rate. We are rarely interested in absolute prices, we're interested in relative prices. So if we compare the price of time at the time t plus delta to the price of time at the time t, then that ratio is 1 over 1 plus r to the power t plus delta over 1 over 1 plus r to the power t, right? That is the relative discount factors at 2 points of time that differ by a factor delta. Now, 1 over 1 plus r to the power t plus delta is of course equal to 1 over 1 plus r to the power t times 1 over 1 plus rho, I should say rho, not r, to the power delta, right? That just follows. And then, of course, we have 1 plus rho to the power t on above and below the division sign. And 1 over 1 plus rho to the power t simply drops out, and the relative price of time is 1 over 1 plus rho to the power delta. And this is very peculiar, right? Essentially what this says, and here I do the same thing but now in continuous time. So if you take this function here, and we typically think of t as the number of years, and then rho is the discount rate per year. But there's absolutely no reason why you would want to do this in time steps of a year. You can do it in time steps of a month or in time steps of a day. That's actually how your bank charges interest to you. Or you could do it in time steps of an hour or a minute or a second, right? And if you and of course, if you use a smaller time step, then your rho becomes smaller, right? Obviously. But if you let the time step go to 0, you go to infinitesimally small time steps, then the limit of this thing, 1 over 1 plus rho to the power t, becomes, by definition, e to the power minus rho t, right? And notation is a lot easier. Now we work in continuous time. The same thing happens here, right? The relative price of time is t plus delta versus t. You can just factor that out. E to the power minus rho t drops out, and the relative price of time is e to the power minus rho delta, the change in time. And this is very peculiar, because essentially what you're saying is that the difference between 11 years from now and 10 years from now is the same as the difference between 101 years from now and 100 years from now, or 1,000 years from now and 1,001 years from now. Which is very peculiar, right? That The only thing that matters is how much time it has passed, but not how far in the future this is. And you can tell the difference between today and next year, right? I would hope. You cannot tell the difference between 21, 22 and 21, 23, right? That's so far in the future that is the same to you, let alone 3022 and 3023, right? It's just blur. So this is a most peculiar property of exponential discounting, right? And indeed, by now there is plenty of experimental and observational evidence that suggests that people do not think this way at all, right? And I show Maureen Cropper here because she was the first to show this experimentally. That this particular property of exponential discounting is just not how people behave and how people think, right? So, what can we do about that? Well, there's one ad hoc solution which follows immediately from the statement that I have here, that it's not the absolute passage of time that matters, it's the relative passage of time that matters. And if something is relative rather than absolute, what you do is you stick in a log, right? Rather than have e to the power minus rho t, you have e to the power minus rho log t. Now, the guy who first did this is Jeff Heel, now at Columbia. When he was much younger than he looks here, and this is an old picture, he was actually at Sussex, but he did other work while at Sussex, not this stuff. So if you take this ratio, the relative price of time, now what we have is that what matters is 1 plus delta divided by t. So the further you go in the future, the longer the time span becomes. And because it's the log, essentially this says that the difference between 10 years from now and 11 years from now is the same as the difference between 100 years from now and 110 years from now, or 10,000 and 1,100 years from now, or 1,000 and 1,100 years from now. Right? That is essentially what this particular intervention does. Now, we no longer have a constant discount rate. We have a discount rate that essentially falls over time. As the time horizon expands, we use a lower and lower discount rate. It sort of works. This is a neat solution, but it's completely and utterly ad hoc, right? So, is there a perhaps better justification for this? And there's two. One is intuitive and the other is counterintuitive. One is intuitive but unacceptable to most economists. The counterintuitive one, as you may have guessed, is the one that economists have embraced. So let's look at the intuitive one first. And that is due to Christian Gaulier, who you see here. So essentially, this is about disagreement. And suppose Miguel wants to discount the future hard, and Emily is much more patient, right? And Miguel says we should use a 7% discount rate, right? That is this column here. So the value of £1,000 in a year from now with a 7% discount rate is £935. In 100 years, the value is only £1, and in 400 years, it's practically zero. Not quite zero, but it gets very, very close to zero, right? Emily is much more patient and says, no, the discount rate should be 1%. So the value of £1,000 in a year from now is 990. In 100 years, it's 370. And in 400 years, that £1,000 is still worth £19. Right? So what can you do if you have two people who disagree about something? You can split the difference, right? That is typically seen as a fair solution. And there's two ways of splitting the difference. The sort of the naive way is saying, well, one says 1%, the other says 7%, so we're going to split this difference, we're going to go for 4%, right? That is what is going on here. Now you may think this is a fair solution to it. 4% goes to 961, 962 after 1 year, goes down to 2/1000 of a cent, of a penny in 400 years. So that's one way of doing it, but that is actually a naive way of doing it, because what enters into our welfare calculations is not the discount rate, but the discount factor, right? We multiply utility not by the discount rate, but by 1 over 1 plus r to the power t times the we multiply the 1 over 1 plus r to the power t, not by r, right? So we can also split the difference on the discount factor. And that is happening in this column, where I simply take the average of this column and this column. And what you see is that in year 1 is 961.5 versus 962.3. Well, it doesn't really make a difference, right? After 100 years, it's 19.8 versus 185.4. Now it actually makes a big difference, right? Whether we split the difference on the discount rate or on the discount factor. And after 400 years, actually it makes a big difference. It's 0.0002 versus 9.3. So it makes a difference, right? And because this is what actually enters into our welfare calculations, this is what we should be doing. Now, if this is your discount factor at all these points in time, then this is the implied discount rate. If we were to discount the future at a constant rate and we would end up at 185 after 100 years, we would have essentially assumed a discount rate of 1.7%, right? And after 400 years, we would have essentially used a discount rate of 1.2%. After 1 year, the difference is very small, 3.9 versus 4%, but after 400 years, it is actually fairly large. And you can actually show mathematically, if you're so inclined, that after an infinite amount of years, this number goes to the lowest number, that is 0.01, right? That is where it converges to. Now this is, can I finish? This is intuitive, because I said, well, we're going to split the difference. And Miguel doesn't care about anything that happens more than 200 years in the future, but Emily does, right? So if we're going to split the difference between Emily's opinion and Miguel's opinion, Miguel doesn't care. So we're going to listen to Emily, right? One is indifferent, the other cares, so you follow the one who cares, right? That is why intuitively you converge to the lowest discount rate in the set. And the implication is that essentially you use a discount rate that falls over time. Shmir.
Can you clarify the difference between discount rate and discount factor?
Discount rate is R, discount factor is 1 over 1 plus R to the power T.
Is R a row?
Or row, doesn't matter. R is for money, rho is for utility. Doesn't matter which of the two you use, the effect is the same, right? So this is the discount factor, this is the discount rate.
And what are the different implications between a rate and a factor?
It's just different name, but I mean they're obviously different, right? One is rho, the other is 1 over 1 plus rho to the power t, right? So that is the intuitive derivation of declining discount rate. Disagreements between people, and you follow the one who has an opinion still. The problem here is that we're comparing the utility of different people, so we look inside their heads how happy they are. and that we can't do. The alternative derivation is due to Marty Weitzman, who you see here. And Marty does it as somebody, we take Marcos, he can't make up his mind whether the discount rate should be 1% or 7%. And then Marcos has two choices. He can split the difference on the discount rate, or he can split the difference on the discount factor. And the result is exactly the same. If you're unsure what discount rate to use, then in the very long run, you would use the lowest possible. Right? So that is essentially Weitzman's derivation, which is mathematically identical, but now rather than have disagreement between two people, we have one person who disagrees with him or herself. Right? The effect is identical. Now, the important thing here is that for short-run investments, you use a fairly high discount rate, but for long-run investments, you use a fairly low discount rate. So if you're thinking about investing in R&D or investing in education or saving for your pensions, well, I'm saving for my pensions, that's a relatively short-term investment, right? You can use a fairly high discount rate. But if you're investing in long-term projects, climate change, nuclear waste, you can use a fairly low discount rate. So you can actually use different discount rates depending on the length of the investment in a consistent way, right? So it's not that, oh, we care about climate change and therefore we should lower the discount rate. And if you lower the discount rate, then we should invest more in education and invest more in healthcare and invest more in road safety and invest more in everything. And then still we won't have any money left to invest in climate change, right? But in this way, you actually can square this particular circle. Now, Weitzman has an alternative derivation where he makes a whole bunch of additional assumptions and says that a discount rate, R or rho, should be this form, alpha over 1 plus beta t. And of course, if your beta is 0, then you're back to a constant discount rate, right, alpha. And this really matters, right? So here we see two derivations of the social cost of carbon, one with a constant discount rate, and then the social cost of carbon is 6.6 or 2.1, depending on the exact discount rate you use. And if we use instead this Weitzman discounting, that 2.1 becomes 88, right? And the calibration here is such that the discount rate that is used here is the same as the discount rate that is initially used here, and then it falls over time. And it makes a big difference, as you can see. Now, this is not hypothetical at all. This is not academics in the ivory tower. The Treasury, His Majesty's Treasury nowadays, has, for long-term projects, also prescribes a declining discount rate over time. Not quite this form, but a step function. And that also makes a difference, right? It doesn't fall quite as steeply in the end, therefore the difference is smaller, but still you go from a social cost of carbon of 7 to a social cost of carbon of 18 under so-called green book discounting. For some reason, the Treasury calls things according to the color of the report in which they published things. The constant discount rate. So a discount rate that is just stays the same everywhere. It actually is spelled out here. So you would stick to the 3.9 throughout time, or you follow the falling one, right? And it makes a big difference, right? No surprise, and it's consistent Chimera.
And what's the gamma distribution?
Gamma distribution, you know the normal distribution.
Yeah.
The gamma distribution is a variant on that. It's probability distribution. And the reason that he picked the gamma is because otherwise the equation would come out all horrible. That was the only reason. So that concludes time. So let's look at space. You do not care about the distant future, faraway lands, or remote probabilities. You need not care about climate change. So let's look at faraway lands for the moment. So the impacts of climate change differ greatly between countries. I've shown you a version of this graph. This is an older version of the same graph. But what we see is that most of the impacts of climate change fall on poorer countries, right? Richer countries see smaller impacts, may even see positive impacts. The impacts are heavily concentrated on the poor. So what do you do with that, right? So initially what people did was they took these estimates, impacts of climate change, in a whole bunch of countries, or sometimes regions. You say, well, this poorest country here, it must be South Sudan or something, suffers 12% of its GDP. We convert it into dollars. We do that for all countries in the world. We convert them into dollars. We add them up, right? And we have a total economic impact of climate change. Now, that may strike you as this is the logical thing to do. We're going to add up dollars. But recall that behind these impacts, there's all sorts of impacts. There's impact on agricultural markets, there's impacts on coastal zones, but there's also health impacts, right? And if you estimate the impacts of climate change country by country, and you use these monetary valuation techniques that we talked about previously, then you're also going to value those health risks and the number of people dying prematurely, and you're going to measure their willingness to pay to reduce mortality risks and morbidity risks. And willingness to pay reflects your ability to pay. So poorer people have a lower willingness to pay to avoid risk of death than richer people. So if you do it country by country and then add up, essentially what you're saying is I care less if poorer people die than when richer people die. That is the implication of this particular procedure. Shamira doesn't look too happy with his implication. And she's not the only one. This was done in a United Nations context, and it created a bit of a storm. There are solutions to this. One Nobel laureate suggested, well, just abandon this whole valuation of things as an empirical exercise and just pick a number and apply the same number to everybody. Which you can't do, right? You can't say, well, my data, I'm going to ignore data. That is not a wise suggestion, Bill. And again, you run into a problem of internal consistency. So if you're going to say, well, we're no longer going to use the empirical value or the local value for the value of statistical life, that is essentially the value that people attach to reducing their willingness to pay to reduce the risk of death. Instead of using a national value, we're going to use a global value, the global average value. Now there you run again into inconsistency, because essentially if you measure the value of statistical life, then in the UK it is, let's make it £7 million that we collectively have decided it is worth to avoid a certain death. Whereas if you measure this thing in Bangladesh, you're more likely to find £70,000 rather than 7 million. So essentially what you're saying is that I care, what is it, 70,000 versus 7 million. I care 100 times more if somebody in the UK dies than when somebody in Bangladesh dies, right? That is essentially what you say. You can say, well, no, that's wrong, right? let's give everybody a value of 700,000 instead. Right? That seems fair. But the implication, of course, is that if the UK government has to choose between investing money in road safety and saving the life of somebody in the UK in 20 years' time, that is worth 7 million, right? If the UK invests instead money in greenhouse gas emission reduction and saves the life of somebody in the UK in 20 years' time, that is because it's a global problem, that is worth only 700,000. So the UK should spend all its money on improving road safety and not on reducing greenhouse gas emissions. Vice versa, the government in Bangladesh, if it invests in road safety and it saves the life of somebody in 20 years' time, that would be worth only 70,000 because it's a local problem. Whereas if it invests money in greenhouse gas emission reduction and saves somebody's life in 20 years' time, that is because it's a global problem, that is worth 700,000. So the Bangladeshi government should put all its money in greenhouse gas emission reduction, right? That is probably not the implication that you want to draw from this, right? So don't use global averages for this. Really, that is a bad solution. Instead, what you can do is use so-called equity weights. And Marcos asked about equity weights before, and now we're there. Equity weights, I don't know who invented them. This was done at a time when economics was poorly documented. It was probably done in the 50s, late 50s, early 60s. But it was introduced into the climate change debate by David Pearce with a little bit of help of Sam Fankhauser and myself. Equity weights work as follows, right? So what we're interested in is the global damage in monetary terms, right? Because we want to impose a carbon tax. So we want this in money terms, in dollars per ton of carbon or in dollars. What we have are national estimates of the impact, also measured in dollars, right? Now, in order to get from the national to the global, we need to make 3 transformations. The first transformation is this one here. You multiply with the marginal utility, the first partial derivative of utility to consumption. And this tells you essentially that $1 to a poor woman is not the same as $1 to a rich woman, right? That the marginal utility of me giving £100 to you is much higher than me giving £100 to Elon Musk, right? You probably feel happy if I do that. Elon Musk couldn't care less, right? So that is the first transformation that you see here. And that is something that is well rehearsed, right? The second transformation is that you say, well, if the utility in country C goes up a little bit, how does that change global welfare? Right? That is the second transformation. And now we have a problem, right? We started in dollars. We wanted to end up in dollars. We first transform to utility, and then we transform to welfare. So you need to transform back by this thing here. And this is essentially the marginal value of the budget constraint. And the question here really is, what if the Martians came along and gave us $1 additional to be distributed fairly across all the people in the world? How much happier would the world as a whole be, right? That is this transformation here. Now, previously I talked about units, right? So we start in dollars, then we multiply with utils per dollar, welfares per util, and then we divide by welfare per dollar. So we're back in dollars, right? Now, if this all sounds very abstract, if we assume a standard utilitarian welfare function, where we add up the utilities of everybody, then this factor becomes 1. That drops out. If we use a utility function with the constant rate of relative risk aversion, your standard logarithmic function or your standard power function, then this abstract and general term becomes this specific term, where the equity weight is global average income over national income raised to the power eta, where eta is again the rate of relative risk aversion, the curvature of the utility function. How does this work? If you're in a country, so eta is positive, right? So if you're in a country that is poorer than the global average, YW is greater than YC, right? That is what poorer than the global average means. So this number is greater than 1. You raise it to a positive power, so you put more emphasis on what's going on in poorer countries. Vice versa, if you're richer than the global average, then YC is greater than YW. This number is smaller than 1, and you attach a lower value to the damages that occur in richer countries, right? That is how this works. And of course, if you set your eta to 0, then all these equity weights equal 1, right? So just adding up dollars is essentially saying, well, my utility function is linear, right? I have no inequity aversion, no risk aversion. So that is how equity weights work. You can derive them in an alternative way. So this is the function that we're interested in, and I copied it here. And we say, well, these damages are of course not damages. This is not money, right? This is really impacts, let's call it the number of people dying prematurely because of climate change, times the value that we attach to that, right? That is what this damage is. Then, what you can say, well, this value, if we assume that that value sort of regularly, in a regular way, value varies with income, then you can write that as, well, this local value of statistical life is really the global value of statistical life times the difference in income raised to the income elasticity, the power of the income elasticity, right? You can say, well, it just varies in a regular way with income. So you can replace the VC with VW times the relative income raised to the power of the income elasticity. If you then further make the assumption that the income elasticity is equal to the curvature of the utility function, so epsilon equals eta, then we are back in the situation where essentially what you do is you take your local estimates of the number of deaths and you multiply it with the global average value, right? So this is an alternative way of getting to the initial suggestion that was done. But you make a couple of pretty hairy assumptions, and the most crucial one is that your income elasticity is equal to the curvature of your utility function. Now there is a relationship between the curvature of your utility function and the income elasticity, as you no doubt recall from Shepard's lemma and all those sort of things, and all that sort of stuff. But this assumption is generally not true, right? So this is an alternative way of looking at it, but
What's
I is the number of people dying prematurely because of climate change. And it's the impact. V is the value of the impact. Does this matter? Absolutely. So I showed you this particular graph before, which had the relationship between the social cost of carbon, the pure rate of time preference, and the rate of risk aversion via the Ramsey rule. Now we introduce equity weights. And let's blow this up. No. So the rate of risk aversion now has two roles, right? This is the curvature of the utility function. This is the rate of risk aversion, the eta that enters into your Ramsey rule, but it's also the eta that enters into your equity weights. And if eta is 0, then the equity weights are all equal to 1, right? Recall that I said that. And you indeed see that if eta is 0, the numbers are identical, right? As they were, right? So equity weighting with everybody getting the same weight or 1 doesn't change things. So let's blow it up now. But the relationship changes, right? So we have the same starting point at eta is 0. Now if we increase eta, two things happen, right? One, we discount the future harder through the discount, through the Ramsey rule, right? And you see that the social cost of carbon comes down. It doesn't come down quite as fast as in the previous graph, right? Here it goes to practically 0 at 1.5. Here you actually see that we're still above 0 at 1.5, right? So it doesn't come down quite as fast. And then you actually start increasing the social cost of carbon as you become more and more averse to inequity. And that actually begins to dominate for a low pure rate of time preference. For a higher pure rate of time preference, initially the same thing happens, but now we actually see that we have not a social cost of carbon, but a social benefit of carbon. We actually fall below 0. And the reason for that is something that I gave you, I think in week 5, and that is carbon dioxide fertilization. CO2 is plant food. CO2 makes plants grow faster and makes them more resistant to drought. Now, what here we have a fairly high discount rate, right? We have a high pure rate of time preference, and then the eta in the Ramsey rule is also high, so we discount the future very hard. And we have high equity weights, so we put a lot of emphasis on what is going on in poorer countries. And CO2 fertilization is good for poor countries in the short run, right? So if we emphasize the impacts of climate change on poor countries for the next 20 years or so, CO2 is good, right? We should pump more of it into the atmosphere. Of course, it's worse, it's bad in the long run, but because we use such a high discount rate, we don't care about the long run, right? That is why the social cost of carbon becomes a social benefit of carbon in this particular calibration, right? So, don't take that as a take-home message, because after the break, and it would really be good to break now, I'm going to reverse this particular conclusion, right, by introducing uncertainty into the whole thing. Risk and uncertainty is always a bit of a challenge, not just to undergraduates of economics, it's always a challenge. But I'll do my best to try to explain this. So you need not care about climate change if you do not care about the distant future, faraway lands, and remote probabilities. And it's the remote probabilities that we're going to talk about now. I disagree, I think for linguistic reasons, with most of the economics profession. Since this gentleman here, Frank Knight, economists make a distinction between risk and uncertainty, where risk is you don't know what the future will hold, but you have a probability distribution function over what the future might be, whereas uncertainty means that you actually don't know the probabilities either. This has always struck me as the wrong way around, right? So when I say uncertain, I actually mean risk. For our purposes, the two are equivalent, because we're not going to go into the unknown probabilities anyway. Now, we talked about the uncertainty about climate change, and I've shown you versions of this particular probability density function before. This is the PDF of the social cost of carbon. and it is uncertain, right? This is for a pure 3% pure rate of time preference, and we just, it could be slightly negative, it could be 50, it could be 100, it could be higher than that, right? We just don't know. But if we believe this particular assessment, we do have a probability distribution function around this, which in this case is a nice bell shape to it. That has immediate implications, and here you see the same information but now in tabular format. Just focus on the 3% pure rate of time preference for now. If we just look at the top of the distribution, the mode, our best guess of what the Pigou tax should be, the social cost of carbon should be, then it's 27. But if instead we look at the average or the mean, because the uncertainty is right skewed, negative surprises are more likely than positive surprises, then it actually becomes 40, right? And this matters, right? Whether we impose a carbon tax of $27 per ton of carbon or a carbon tax of $40 per ton of carbon, climate policy will be more stringent, emissions will fall harder. So that is the first very basic insight. Because there is uncertainty about everything that has to do with climate change, from future emissions to the response of the climate system to the impacts of climate change and how we might value those impacts, because all these things are so uncertain, and because the uncertainty is asymmetric, that is, negative surprises are more likely than positive surprises, we want to work harder on climate policy than if those uncertainties were not there, right? So that is the very first point that I want to make, and it's probably the most important point I want to make. Now the second point is a bit more involved and tends to confuse people. Von Neumann Morgenstern in 1944 showed that if you're uncertain about stuff, then you should use not the best guess, the mode, you should not sort of pick the middle of the distribution, the median, but really you should focus on the expectation, the mean. And you would be tempted to do it like this, right? Where you say, well, we're uncertain about the impacts of climate change, we're uncertain about the damages, D. So let's say we have, and in the seminar, in the computer lab, we use 3 states of the world. We define the damages in 3 alternative states of the world. We denote that by S. Then we attach a probability to that state of the world occurring, P of S, and then we sum over that, and that is our expected damage, right? Now, you may be tempted to do this particular thing. But you would be wrong, because we do not do welfare calculus in money space. We're not interested in maximizing money, we're interested in maximizing income or consumption. We're interested in maximizing utility, right? So you should not do these calculations in money space, you should do them in utility space. So really what you should calculate instead of the expected damage is, and you still want the carbon tax, right? And we're not going to tax happiness, because you can't do that. You can only tax income, or you can tax emissions, but you can't, or energy use. You can't tax people's happiness. So if you're interested in a carbon tax, then you can't do it in utility space. You need to do it in money space, right? That is the so-called certainty equivalent damage. So essentially what you do is, instead of calculating the expected damage, you calculate the expected loss of utility in all the states of the world as calculate utility in all states of the world depending on the impact that is going on, multiplied with the probability, Then you have your expected welfare loss. But we want things in money because we want to impose a tax in money terms. So what you then need to do is apply the inverse of the utility function to convert things back to money. Now, this is known as the certainty equivalent damage. The difference between the certainty equivalent damage and the expected damage is known as the risk premium. And you by now think I have a hole in my head. You may have thought that already, right? Because what do I do here? I apply the utility function to those damages, and then I apply the anti-utility function to that utility function. So U cancels against U inverse, right? So I took a simple equation, I turned it into a complex equation, but really I applied a function and then the inverse of the function. So what did I just do, right? Yeah, silliness. Just make things complicated for no reason. Well, not quite. So let's look at some numbers. So we start here where we have an initial income of 1,000. And the initial situation is that there's no climate change, so there's zero damages. So we have an income of 1,000, we don't lose anything, so our utility is 6.91, right? Then there is a 50% chance of losing 10, and there's a 50% chance of losing 20 out of that 1,000. So 1,000 minus 10 is 990. Take the log of that to get to the utility, that's 6.90. 1,000 minus 20, 980, take the log of that, that is 6.89. What did we just do? Well, 50% chance of losing 10, 50% chance of losing 20. The expected damage is 15, right? If we take the average of 6.9 and 6.89, I dropped a couple of significant digits, then actually the average is 6.89 of these two. It's a little bit closer to the second one than to the first one, that's why we round down. Take the anti-log of that, take the exponent of this, we have the equivalent income, right? That is 984.99. So our loss, our certainty equivalent damage, is 15.01. Compared to the 15 that we had here, the risk premium is 0.01. So you're perfectly right in saying, well, taking the utility function and then the anti-utility function, you did not change anything, right? You changed things sort of behind the decimal point. Well, true in this case, right? What's the point of doing this? If instead our initial income is not 100, is not 1,000, but it is 100, then we're in this column, we do the exact same range of calculations, the expected damage is still 15, but if you take the average of this, convert it back to income, now our certainty equivalent damage is 15.15, and our risk premium is 0.15, 1%. That justifies such a complicated calculation? Well, maybe, maybe not. Now look at this different scenario here, where there's a 50% chance of losing 10 and a 50% chance not of losing 20, but of losing 98. The base income is 1,000. We do the whole calculations again. The certainty equivalent damage is 55.02, which is 1 greater than the 54 than we had there. This risk premium is still fairly small, right? But if instead we compare this to an income of 100, now there's a 50% chance of losing 10% of everything we have, but there's also a 50% chance that we lose 98% of what we have. Then, of course, utility tanks in the second, the bad scenario, right? Our expected utility is 2.6 only. The equivalent income of that is 13.42. And our certainty equivalent damage is 87 rather than the expected damage of 54. And the risk premium now is very, very large, right? Relative to the expectation. So this theoretically consistent calculation, compute the certainty equivalent rather than the expectation, do the evaluation in utility space rather than in money space, matters when risks are large, right? Large relative to your starting point. And that is shown in this graph. I showed you just two examples right here. Now we go continuous from there's a 50% chance of losing £10 relative to an income of 100. And then there's a 50% chance of losing nothing all the way up to 100, right? And then you see, well, this is the risk, this is the expected damage. Just increases linearly. The certainty equivalent damage, the difference between the two lines is risk premium, increases more than linearly. And if, as we get closer to almost losing everything, it starts to diverge very, very rapidly, right? And of course, if you go to 100, then we lost everything, right? So if we have a utility loss of that is infinitely high, right? A utility becomes minus infinity. That's not shown on this graph because I can't draw that.
Dashed line certainty.
Certainty equivalent damage, expected damage, right? So these things matter if there is a chance of losing it all, right? Then the difference between certainty equivalent and expected damage becomes very important, and you should do the theoretically correct way of calculating expectations in utility space rather than in money space. Now, what does this do to the social cost of carbon if we introduce these uncertainties? Well, I showed you this graph before, right? Where we just had time, right? Just time discounting. We did not care about the distribution of the impacts. We just looked at rate of risk aversion as it guided the Ramsey rule and the pure rate of time preference. Those were the two things that we cared about. Now we're introducing parametric uncertainty or risk into the model, and we start with a rate of risk aversion of 0. We actually don't care about the uncertainties, right? We're risk neutral. And what you see is it actually doesn't affect the results at all, right? We're still, the starting point is exactly the same. But then as we care more and more and more about the risks, you actually see that the social cost of carbon doesn't come, it still initially falls, right? And because we discount the future harder because of the Ramsey rule, but it doesn't get anywhere near 0. Here it goes very quickly to 0 at 1.5. Here it does not, right? So the social cost of carbon is indeed larger because we care more about risk. And then what you see happen is that if we become more risk averse, the social cost of carbon starts to increase and increase very rapidly, right? I cut it here off at 1,000. It just keeps on going up and it actually asymptotes. And you see that better in this particular graph. So the rate of risk aversion here really, really matters, right? We can essentially justify any carbon tax, an arbitrarily high carbon tax if you like. Which leads me to the most difficult concept of the entire module, and that is Marty Weitzman again, right? So this is the third time we meet Marty. So the Nobel Prize for Economics in 2018 went to Bill Nordhaus, right? Who we also met. He was the first to do a cost-benefit analysis of climate policy. We did not meet Marty Weitzman, or Marty Weitzman we met as well twice before, sorry. He did not get a Nobel Prize, right? Which really, really affected him and made a lot of people very, very cross, including me. We met Weitzman as the father of prices versus quantities. Should we use a carbon tax or should we use tradable permits? That was Weitzman, that was a younger Weitzman. We met Weitzman before the break for his contributions to discounting. Now we're going to meet him again for his contributions to decision making under uncertainty, right? If we were to do, had the opportunity to do environmental economics, you would have met Weitzman a fourth time for his contributions to national accounting. And if you were to do biodiversity conservation, you would have met him a fifth time, right? For his Noah's Ark work. So Weitzman is by far the intellectual superior of Nordhaus, right? But the Nobel Committee thought differently. Much to his dismay, he eventually committed suicide. And that was not the response we had hoped, but most people thought it was unfair, including Nordhaus, right? Nordhaus also was very clear that this prize should have been shared. Anyway, so much for biography. Weitzman and his dismal theorem is a very complicated one. Essentially, the dismal theorem says that the uncertainties about climate change are too large for expected utility maximization. You can't do cost-benefit analysis on a problem as uncertain as climate change, is essentially what the dismal theorem says. Now, Weitzman's derivation is beyond undergraduate economics. Actually, it's beyond PhD in economics because it works, it's essentially probability calculus. So it works through convolutions and moment-generating functions, and I won't bore you with that. But there are two simpler derivations, one by me and one by Kato. If we take the Ramsey rule, right, then we say that the consumption discount rate is the pure rate of time preference plus the curvature of the utility function times the growth rate of the economy, or the growth rate of consumption. And so far I've always said, well, G is positive, right? The economy is growing. But what would happen if, because of climate change, the economy starts to shrink? Some people believe it will. Now, if G becomes negative, then you don't discount the future so hard, right? One of the reasons that we discount the future is that because we expect to be richer in the future. So it doesn't make sense for you to save money to transfer to a future richer self. That's just a silly thing to do. But if you expect to be poorer in the future, then it does make sense to start saving and transfer money to yourself. And that is indeed what people do in preparation for their pensions, right? When they retire, they save money to transfer to their poorer selves in the future who don't have an income anymore, right? So then it makes sense to start saving. If your G becomes very negative, if your G is smaller than minus rho over eta, then essentially you would use a negative discount rate. And a discount rate is called a discount rate because we discount the future. If we have a negative discount rate, then we put a premium on the future, right? The further things are in time, the more important they become. And then essentially what happens is that, I talked about it yesterday in class, your net present value function becomes infinitely high, right? Because every time you add a year to your time horizon, things are more important still, right? And you should keep on adding things to your future until everything becomes infinitely large, right? And the same is true for your social cost of carbon, right? We also cut the social cost of carbon after the year 2300 because of discounting didn't matter anymore. But if we have a negative discount rate and a discount factor that grows over time rather than shrinks over time, then also our social cost of carbon just keeps on going up and up and up and up and up and up. If we add more years, as we add more years to our time horizon, and we have an infinitely large carbon tax, right? So that is one derivation. The other derivation is due to Susumu-Kato. This is not Susumu-Kato, this is Jacob Bernoulli. And it's known as the Petersburg paradox because Jacob was visiting his uncle Daniel in St. Petersburg, right? Peter the Great had just started St. Petersburg and had just started the university there and was attracting scholars from all over Western Europe to teach there. That is why the two Bernoullis were there. And Jacob suggested the following paradox, and this is 1768, I want to say, definitely late 18th century. So suppose that somebody comes and offers you a game, right? And the game is as follows. I'm going to toss a coin. If the coin lands on its tails, the game ends, right? If it lands on its head, then we're going to continue the game and we're going to double the stake, right? And the initial stake is £2, right? Just for the sake of simplicity. Then what is the expected payoff of this game? Well, in the first round, right, there's a chance, it's a fair coin, a chance half that it lands on tails, half that it lands on heads. So your expected payoff is £2 with a probability of 1/2, so that is £1, right? But then if it does happen, then the game continues, right? And the stake doubles, so in the second round you would get £4. But of course the probability of it landing twice on heads is only a quarter, right? 3 times it's 1/8, but the stake has doubled, so you win 8, right? And so on and so forth. So your expected payoff is 1 plus 1 plus 1 plus 1 plus 1 plus 1. It's infinitely high, right? So logically, the payoff of this particular lottery is infinitely high. So you should be willing to pay everything you have in order to enter this lottery, right? Everything you have and everything you can borrow, steal money from your parents. This is what you should be willing to pay. Obviously you're not, right? Obviously you're not, because giving up everything is a certain loss. And even if you're worth only £30,000, right? Make a stab. You guys have borrowed so much money, you're probably worth negative 30,000, right? Even if you were worth £30,000, you would not be willing to give up £30,000 to do this. A certain loss of £30,000 versus a chance of winning a gazillion pounds is not something that you would enter into, right? And the explanation for this is risk aversion, right? We don't look at these sort of probabilities in money terms, but we use it in utility terms. And yeah, there's a small chance of winning a lot, but it is not worth that much, whereas giving up everything certainly costs you a whole lot, right? So this is the foundation, the intellectual foundation of risk aversion, right? And it goes back all the way to, I believe, 1768. This letter that Bernoulli wrote to his, I think it was his father, back in Zurich. Now, I promised you Susumu Kato, here he is. He actually has an alternative derivation of the dismal theorem. So, there's a 50% chance of losing half of everything you own, a 25% chance of losing 75% of everything you own, a 12.5% chance of losing 87.5% of everything you own, and so on and so forth, right? A 2 to the power minus k chance of losing 1 minus 2 to the power k of everything you own. So what is your expected loss? Well, half a chance of losing 50%, so that is 1 over 2 times 1 over 2, right? 1 over 4, 25% of losing 75%, so that is 1 over 4 times 1 over 4, or 1 over 2 times to the power 4, right? 1 over 2 to the power 6, and so on and so forth, right? The expected value of this, the expected loss, is 1/3. That doesn't seem at all right, right? If I were to ask you, okay, I'm going to confront you with this is going to happen. Now, how much are you willing to pay to get out of this scenario? You're not going to say, I'm going to give you 1/3 of everything I own, because the consequences here are just so horrendous, right, that you would be willing to pay a lot more to get out of this situation than 1/3 of your income. Because really, this is destitution, right? So if you then introduce risk aversion, you say, well, it is -2, I'm actually gonna not evaluate in money space but in utility space, then it's still 1/2, 1/4, these are still the probabilities, but the loss now is -2, -4, -8, rather than half of the income, and your expected utility of this particular scenario is -infinity. In other words, dismal theorem is just a corollary of the St. Petersburg paradox. Whereas the St. Petersburg paradox is, are you willing to enter into a particular gamble that has an infinitely high payoff, but you're willing to pay less than everything you own to enter into this gamble? The expected loss of this particular scenario is not 1/3, it's actually infinitely high. And you would be willing to give up everything to avoid this particular scenario, right? And that is essentially what Weitzman said, that the uncertainty about climate change is such, and the impacts of climate change are such, that we're somewhere here, right? Where our utility or our certainty equivalent damage really strongly deviates from our expected damage, so that we're really, really, really risk averse. And really the carbon tax that we want to impose is very, very high. Right? That is essentially the dismal theorem. Or as Weizmann says, the Pigou tax is arbitrarily large. Time. Now, when Weizmann wrote this, published this in 2009, this actually caused a bit of a stir. And there's been many interpretations of what he meant to say, and so on and so forth, rather than just listen to what he had to say. He was a pretty vocal guy. So some people see this as a formalization of the precautionary principle, others see it as a justification of stringent climate policy. But when you strictly read what the dismal theorem says, is that things explode. You can't really have an arbitrarily high carbon tax, or you can't really use cost-benefit analysis for a problem like climatic change. And the reason that you can't do this the way some people have read it, that the Pigou tax should be arbitrarily large, that we should have a very high carbon tax, is because definitely in the very short run, fossil fuels are an essential input to the economy. So what does an arbitrarily high carbon tax mean? It means stop using fossil fuels. Not stop using fossil fuels in 2050 or in 2080. No, stop using fossil fuels on the 30th of November 2022, right? Now, what happens if we stop using fossil fuels? Well, the lights go off, right? And you can't, so that's pretty awkward, but it's light outside, so that is fine. Heating will also go off. That is more awkward. Your phone can no longer be recharged, so you can no longer talk to your friends and family in 8 hours from now. That's actually not true, because those masts also require electricity, so you can no longer talk to people from now onwards, right? So it all becomes pretty costly and pretty awkward. But there's actually more that would be going on. If we stop using fossil fuels, then you cannot transport food anymore from where food is grown and stored to where the people are. So you would have widespread famine within days, and you would have a large number of people starving to death within weeks. That is actually not true either, because it's not just that the food production stops and food transport stops and food storage stops, but also we would stop purifying water. And you guys, most of you guys have grown up, maybe all of you guys have grown up with clean water, and drinking dirty water would kill you within a week, right? So if we impose an arbitrarily high carbon tax, then the forecast is that within a week 6 billion people would be dead. And probably within a month 7.5 billion people would be dead, right? So that cannot be the policy recommendation, right? It cannot be that because of climate change we want to kill off most of the world population. But that is essentially what the dismal theorem says, that the carbon tax should be arbitrarily high, right? So really what the dismal theorem tells us is that we cannot do expected cost-benefit analysis. And instead, we should look at alternative decision criteria. And that's why I hesitated. We have 20 minutes left, so I can do this. So this guy here, who really looked like that, his name is Savitz, but I forget his first name. I think it's Will Savitz. But don't cite me on that. Suggested that instead of looking at maximizing expected net benefits, we should minimize the maximum regret. And essentially what you do is actually what we've been doing for this week's assignment. By definition, if you're uncertain, you have all sorts of alternative futures, all sorts of alternative states of the world, right? Climate sensitivity can be middle, the climate sensitivity can be low, can be high, right? That is the state of the world. So what you do in first is that for each of these possible worlds, each of these possible states of the world, you ignore the uncertainty and just find your optimal course of action, the optimum carbon tax. Then you redefine your objective function. Instead of maximizing utility or maximizing welfare, you say, we're going to look at regret. How far am I from the optimum? And your distance from the optimum, from your maximum utility, that is what you call regret, right? And you do this for every possible state of the world. Then you reintroduce uncertainty, and then what you do across your uncertainty is you find what is the action that would cause most harm, where my regret is largest, and that is what you want to avoid, right? Instead, you want to focus on that action where your regret is minimum, right? And that is known as mini-max regret. And if you do that, you can't find a maximum with a continuous problem, you end up in situations like this. So in blue, we're looking at net present value, global, as a function of the carbon tax on the horizontal axis. And we're just going to find the expectation of this, and we're going to pretend that the dismal theorem doesn't exist, right? So what you see is if you have a zero carbon tax, then this is your net present value. Then if you increase your carbon tax, then welfare quickly improves. We find a maximum at some point, and then things start falling again, right? And that is why there's an optimum. And here, what you say, if you go to a carbon tax of 350 or so, then you say that the climate policy is more expensive than the avoided climate change can justify, right? That is how you find the optimum. In green and in red, you're looking at the regret function, and the regret function is something that we want to minimize. And you have the median, the 75 percentile, 90 percentile, and so on and so forth, all the way up to the 99.9 percentile. And the regret function has a very similar shape, right? No climate policy, a lot of regret. Then if we introduce a little bit of climate change, we're actually going to reduce regret. And at a certain point, climate policy becomes more expensive. It increases regret again. And also the regret function, except for the very high percentile, has a clearly defined minimum as well. That is not too different from the one that maximizes utility, right? So the upshot here, the real implication of the dismal theorem is if you can't use expected cost benefit analysis, then you should use something else. And Savage's criterion is one alternative. But the fact of the matter remains that, yes, there is such a thing as dangerous climate change. There is sort of like a 7-degree warming of the planet is definitely something we want to avoid. We don't want to go there. But there is such a thing as dangerous climate policy too, right? And just because the uncertainties are very large, it does not mean that this particular risk disappears as well. And you need to continue to balance the two risks. Right? right? People are beginning to look dubious.
No, no, the notes aren't uploaded. The lecture slides.
They're. I was doing other things this morning. I pointed at Yinchi, but I was actually doing other things this morning. I was speaking in Tokyo this morning. So now let's put everything together. And in the last 15 minutes. So we started with this particular graph, right? Where there was no uncertainty, there was no concern about equity, and we just had concern about time. Then I introduced this particular graph where there was equity as well, and what I said that for relatively low rates of risk aversion, you actually have a higher social cost of carbon, but you may have a higher social cost of carbon if you have a low pure rate of time preference, but for higher pure rates of time preference, we actually put a lot of emphasis on the positive impacts of climate change in the short run in poorer countries, right? So we have a social benefit of carbon. Then I did away with equity again, and I introduced uncertainty, and now here we are very risk averse. We put a lot of emphasis on the bad tails, on the bad things that might happen because of climate change. And we have a very high social cost of carbon for high rates of risk aversion. Even though we discount the future very hard, the concern about things going drastically wrong are much more important than that, right? And now the final question remains is, what if we introduce uncertainty here, or what if we introduce equity here, right? And that is the final graph that you see. And this graph looks much more like this graph than like this graph, right? So concerns about uncertainty dominate concerns about equity quite strongly, and actually they amplify each other. If you look closely at this, you can see it best in the blue graph. Here we sort of like begin to asymptote at the very end. Here we go up much more rapidly, right? Because we still have those positive effects of CO2 fertilization in the short run, but in the long run you have really negative effects potentially on poor countries, right? And they are much more important than the short-term gains, even if we use a fairly high discount rate, right? Here we really start to emphasize the bad risks for poor countries. Here we also have bad risks, but here we emphasize the bad risks for poor countries. And you see that the social cost of carbon can be fairly high. So this effect, though, that social benefit, right, that is an artifact of ignoring uncertainty, right? So don't go telling people that I said we should be subsidizing CO2 emissions. That's not what I said. Which leaves me the final question. What should we do, right? What we now have is that depending on the pure rate of time preference that we use, 1%, 2%, 3%, we get a different answer for what the carbon tax should be. And depending on the rate of risk aversion that we choose, 0.5 or 2, we get a very different answer for what the social cost of carbon should be. And not a little bit different, right? A lot different. What we see here are values that are close to 0, and we see values that are greater than 1,000, right? So, what should we do? Now, I've started this discussion already, right? So I can be relatively quick. So these ethical questions are crucially important, right? And you cannot avoid them. Now there's two ways of doing this. I prefer to do it like this, right? To say, well, this is the mapping of the pure rate of time preference and the curvature of the utility function to the social cost of carbon. And even though I have opinions about the pure rate of time preference, and even though I have opinions about the rate of risk aversion, it is not for me to decide what these values should be, right? Because I'm just one guy in 8 billion nowadays, right? It's not for me to decide this. And that is, I think, the role of policy advice, right? Tell people what are the trade-offs, how certain assumptions that may be disputed translate into certain results, right? But it, of course, does not take away the social question that we should pick those parameters, right? Now, there's an alternative you can do. You can say, well, I think that a carbon tax should be $100 or $200. That's easier on the graph. And therefore, my pure rate of time preference is 1, and my rate of risk aversion is, what is it, 0.35? That is, of course, what you can do, right? But that is not valid, because you start with the conclusion and you work towards your assumptions. But really, you should pick these numbers somehow. And as I said before, there's two approaches to this. One is to follow thought leaders. And I talked about Socrates before, right? How Socrates was dead against usury, dead against levying interest rates. And you can say, well, Socrates was a pretty smart guy, and St. Augustine believed what Socrates said, and I'm a Catholic, so I'm going to do what St. Augustine said. Or you could say, well, Mohammed believed what Socrates said, and I'm a Muslim, and I'm going to follow this guidance, right? That would be acceptable, right? But yeah, why Socrates, right? You can say, well, he was a pretty clever dude, right? But he's also, I mean, he has been dead for 3,500 years. And if you read what he thought about slavery, or if you read what he thought about women, then you say, oh, I actually don't agree with this guy. So why would I agree with him on discounting, right? And on the discount rate. There's other thought leaders who you might feel closer to, right? Jesus is there, Lao Tzu is there. You may say, well, I believe what Johnny Rotten says about these things, right? It's better to burn out than to fade away. It's of course not what Johnny Rotten did, right? Johnny Rotten is busily fading away, never burned out. Or you may follow what Lady Gaga, here shown with her rightful place in history, says about these things, right? Lady Gaga is absolutely silent about risk aversion and about time preferences, but she has pretty strong opinions about how we should treat others, right? So that is one approach, right? And that's up to you whether you want to follow this and who of these people you want to follow. And there's probably a whole bunch of other people that inspire you, right? And the alternative, as I also said, is just to measure what people do and say, well, I'm going to somehow take the average of people's preferences. Now, had we had another week, then I would have talked about the measurement. What you can do next term is follow behavioral economics, where George will explain to you in excruciating detail that it's actually very difficult to measure somebody's time preference, right? So you could sort of look at yourselves, right? What you've done is 3 years ago, 2.5 years ago, you decided to go to university and study economics, which is an investment in the future, right? So you could sort of like say, well, this implies a time preference, right? You gave up 3 years of earning in return for what you hope would be a much higher salary and a more fulfilling life. because you have a more interesting job with a degree than without. So you can sort of say, well, this is an investment that I make, and this implies a pure rate of time preference. When we interview first-year students of economics, what they expect their income to be after they graduate, and compare that to their actual income after they graduate, there is a huge divergence there, right? So people make these decisions based on imperfect information. And of course, what you have learned over the 2.5 years, almost 3 years that you've studied economics, or been at university, is that things were not quite as you expected them to be 2.5 years ago, right? Economics is very different. Studying is very different than you anticipated. You have probably completely changed, because that's what people do at this stage of their life. They look at things very, very differently when they're 20 than when they're 18, right? So you have misinformation, you have a lot of uncertainty about, because I mean, when you entered into university, there was no looming recession, right? When you leave university, we are in a recession, right? That's something you did not count on, I think. So, yeah, you made a decision to invest in your future, but that decision was made under very strange circumstances. Your parents were talking to you, your friends were talking to you. That it's actually very hard to pinpoint what parameter values guided my decision. Now, this is perhaps an extreme example, but whenever you look at people making intertemporal decisions, we make such decisions all the time, or whenever people make decisions under uncertainty, which we do every time, right? You don't know what will happen when you cross the road or when you get out of bed in the morning, right? Or when we make decisions that sort of imply redistribution of poorer people to richer people, or from richer people to poorer people. There's always so many things going on that it's actually very difficult to measure people's preferences. So even if we could, we would do that, we would still have a problem aggregating them. But it turns out that it's extremely difficult to measure these things. So for that reason, we're sort of left in the dark here, right? And this is a very unfortunate conclusion to this. That, yeah, it hugely depends on what row you pick and what eta you pick and what row you pick. We actually don't know what those values should be, right? Final words, consistency here is crucial, right? So if you're very risk averse in one domain, it doesn't make any sense to be less risk averse in a climate domain. Or if you use a very high discount rate for investing in education, as the UK government actually does, then you should not use a very low discount rate if you're investing in climate policy. That doesn't make any sense whatsoever. Or if you're perfectly happy that over the last 10 years, 35,000 people drowned in the Mediterranean on their way to Europe, as they did, then it's very strange when you turn around, oh, but what would climate change do to these poor souls, right? So consistency here, I think, is very important. Well, I actually think that we should care about the impacts of climate change in Africa, and we should also make sure that these people don't drown in the Mediterranean. Which I think is a consistent preference. But those people that say, oh, I don't care about them drowning, but I do care about climate change, I think is a very strange thing to say, right? So, not a very conclusive conclusion, but unfortunately, that's where we are. So we have 1 week left. Next week, we're going to do, finally, game theory and international environmental agreements, right? Where we have not one philosopher queen, but we have 200 of them. And we're going to see how they're going to try and coordinate their actions.